Here we're going to show you your first CUDA program. Most of the CUDA tutorials on the internet and on the video's website are pretty much the same. But we're going to vary this a little bit, perhaps provide a little more information. We're going to work with both a vector, one-dimensional matrix, and a two-dimensional matrix. This will help your understanding of threads and blocks. Okay, so looking at the diagram here, a grid is a collection of blocks. The hierarchy of elements is a grid is a collection of blocks. The blocks is a collection of threads. A thread you can think of as a CPU. It has its own register. It does its own math. Okay, but it produces a scalar. Okay, this function increment is called a kernel function, meaning it runs on the GPU device. We denote that by putting the underscore global out in front of it. If you look at this diagram, there's 5 threads in X. Okay, there's only 1 thread in Y. The block dimension is 5. I made it the same size as the 5x1 vector to make it easy to understand. Normally you would have more than one block above this block, so that you would then have to multiply the length block of the block by the block position, then add threadIdx.x to get the location or the offset in the current block. This multiplied together, you can think of that as how many blocks are above this one. Then you add threadIdx.x, which is the offset in the current block. Okay, this is our setup code in main. We have 5 threads. We initialize the host array to hold these 5 values. Then we create the structure C host array to receive back the resulting values when we increment each. Okay, we use CUDA malloc to allocate space on the GPU. The pointer to that is star D device array. Obviously, it's the size of int, because we're putting integers into each element, times the number of threads. Then we copy the data from the CPU to the GPU using CUDA memcopy. We say the target, D device array, the source, H host array, and then the same calculation for size. And then here, CUDA memcopy host to device gives the direction. When we bring the data back down, we'll use CUDA memcopy device to host. Here I set number of threads to 5 because I have 5 elements in my array and I want 1 thread per element. Then I create a grid with just 1 block and a block that contains 5 threads along the x-axis. When I launch the kernel function increment, the GPU creates 5 parallel threads. Each one gets a different threadIdx.x from 0 to 4, and each thread increments its own scalar. The rest of the code just copies the array from the GPU back to the host array and then prints out the results and frees the memory with CUDA free. Okay, here is our setup code in main. We create a 5x2 matrix. Next, here's our kernel function. Remember, it does not store the matrix elements. It just retrieves them from GPU memory using the row and column locations. Then it writes the scalar back to the GPU location pointed to by the pointer. In our example, it's D underscore device underscore array. Okay, now we call the kernel function. Each block size is row, column. The threads in the block have the coordinates row, thread ID X, thread ID Y. For a 5x2 array, you can think of threadIdx and threadIdy as columns inside the block and rows inside the block. Okay, here each thread corresponds to exactly one array element. The thread is just a worker for that element. It's not a container of 2D objects. Okay, now for grid size. Okay, we use a general formula to compute the minimum grid size needed to fit a thread for every element. It calculates, okay, how many blocks do I need to cover all row times element, row times column elements.